So during my talk, I'm going to focus on among the many different applications of machine learning to chemistry that we have been pursuing in my lab over the past few years. I'm going to focus in particular to the applications that go beyond the construction of a force field. And to give a little bit of motivation, I mean, the broader motivation why I got into machine learning is really because deep down my interests involve modeling physical processes in materials and for molecules. And in particular, my ambition would be to go beyond the prediction of single point properties for ideal geometries, but really to sample the distribution of configurations that is associated with certain finite temperature conditions, to incorporate defects, interfaces, and all of these together with the need of evaluating the properties of individual configurations with predictive first principles accuracy lead to a cost that even with the real machines is prohibitive, or still, I mean, it's a very inefficient use of electricity and a very inefficient way of generating CO2. So what machine learning does promise is to sort of cross the cost accuracy landscape and reach an optimum spot in which after having trained the model calculations, it can reproduce the accuracy of empirical models at a cost which is much reduced relative to an explicit solution of the electronic structure problem. Now, this has, this kind of dream scenario is now essentially reality when it comes to the evaluation of energy and forces. Of course, there is still a lot of work to do to iron problems out, to make things better, but the general idea is basically there, and it's now quite well established. And the point I want to touch upon in this presentation is that there is more to life and reality than the energy and the forces. And I want to show this as an example. This paper to which I contributed a little bit from the group of Vadim Rybkin, where they performed simulations of a solvated electron in water using a machine learning potential fitted on MP2 energy and forces. And what I found really well, I mean, it's a very nice paper and it's a very nice findings, but what struck me was the fact that after having run DMD trajectories using this machine learning potential, in order to be able to visualize the excess electron, so the spin density associated with the excess electron, they had basically to go back and run a few hybrid DFT calculations to determine the actual spatial extent of the solvated electron. And this is because the machine learning model was doing very well in reproducing energy and forces, but was not capable of describing the spin density of the excess electron. So this led me to think that we need models that, just as electronic structure theory, give you access not only to energy and forces, but to whatever physical property you might need to be able to compare with experiments and to understand the physical processes that are at play. Now, before I get to this, I need a short preamble on a fundamental mathematical problem of the machine learning of molecular and material structures. And as you will see, these mathematical developments are essential to be able to build models that go beyond the energy, forces, and stress paradigm. And so what I'm going to discuss in this section is basically the problem of building representation. So by representation, I mean a mapping between the Cartesian coordinate of the atoms, the structure of a molecule, and a more or less abstract vector in feature space that is the object that really goes as the input of whatever machine learning model you want to build. Now, if you want to have a representation that then gives rise to an efficient, data efficient, first and foremost, machine learning model, there are a number of requirements or desirable features of this mapping. First, which might seem trivial, but actually is not, is that to have a mapping that is complete, meaning that if I have two distinct structures, they should map to different vectors in feature space. And what makes this completeness requirement far from trivial is the way it plays along with a second requirement, which is that of being symmetric. So you want this mapping to be such that if you have two structures that are just symmetry copies, and by here I don't mean a special symmetry, a point group symmetry or anything, just I rotate, translate the structure or permute the indices of the atoms, these should map me to the same point in feature space, because then the machine learning model, without any effort in the construction of the architecture, will be capable of doing exactly the same prediction for these structures that are all symmetric copies of each other. Then we typically want this mapping to be smooth, and something that I will not have too much time to talk about, but is, in my opinion, essential to the construction of transferable models, is that of having a mapping in which a structure is described in an additive manner. So essentially, the entirety of the structure is broken down in a sum or a combination of representations of atom-centered environments. Now, with this set of requirements sort of acting as a force driving the evolution of the field, the community has generated a very large number, and it's basically every day there is a new paper introducing a new representation that maps the Cartesian coordinates to the input of a machine learning model. And in this review and in this picture, we try sort of to put some order into this zoo of representations. And actually, one of the things that we realized is that a very strong ordering principle to sort of classify these representations involve focusing on the symmetry operations that are used to go from Cartesian coordinates to the actual structure. And furthermore, another thing that we noticed is that even though they might differ in their construction and in the mathematical procedure by which you obtain them, by and large, the majority of the features that have been most successful can be regarded just as different routes to get to the same point. So basically, pretty much all the representations that you see here at the leaves of this tree can be obtained from one another in the complete basis set limit, just as a linear or nonlinear transformation. So with this idea in mind, we basically developed a general theory of representations that describes how you can construct any of these as a sequence of symmetry operations. So starting from the Cartesian coordinates of the atoms that are obviously complete, but they are also obviously not symmetric in the sense that, for instance, if I swap the labels of two carbon atoms, I will swap their rows in the Cartesian vector, and therefore the vector will become different, and the machine learning model will have to learn that the energy doesn't change depending on the order by which I list the atoms. So a first step in a general construction of representations is to build a field, a density, effectively, that it's a function of R3, which is constructed as a sum of local functions centered on the atoms. This could be deltas, Gaussians, or if you are particularly masochistic, any other localized function. And once you have done these, you look at how the structure is represented. That is represented as a three-dimensional field. And from the position of the peaks, you can very easily, but don't specify anymore whether this is carbon 1 or carbon 176. And so by this density field construction, we take care of permutation invariance. We don't, however, take care of the invariance to rotations and translations, because if we change the reference system, this becomes a different function over 3. So this field is not translationally and rotationally symmetric. So how can we make it translationally symmetric? For instance, well, a relatively simple way is to actually symmetrize over translations and rotations. And I don't have the time to really get into the details of the procedure, but basically the result of this procedure is that you associate with each structure basically with each atomic environment, you associate a hierarchy of correlation functions of this environment-centered density. And this hierarchy of correlation functions provide you a linearly complete basis to expand any function. So at least in principle, this basically gives the most complete possible featurization of the structure of an atomic environment with a finite extent. Now, what is very nice is that, again, just to whet your curiosity, if you are interested, you can look at this paper, which is where we introduced the framework, or you can look at the review that is a little bit more pedagogic. But essentially, this hierarchy of density correlations, which is really, you know, the same kind of correlations that you use to describe the statistical physics of liquids. If you use it as a linear basis, it generates a body-ordered model of your target property. So if you take the first order correlation that is essentially equivalent to a pair correlation function, you use it in a linear regression model, you obtain the most general form of a pair potential. And the same goes for the 3-body, 4-body, 5-body, and so on and so forth. So these can also be extended, this same construction can be extended to build features that are not invariant to translations and rotations, but are equivariant, meaning that basically you can build not only a hierarchy in body order, but also a hierarchy of features that transform like scalars, so like a L equals 0 spherical harmonic, or as a vector, L equal 1 spherical harmonic, or as L equal 2, L equal 3, and so on and so forth. So one possible extension of this construction basically goes from the construction of invariant features to the construction of equivariant features that will be central to the prediction of properties beyond potentials. Another extension that we have been working on is basically to overcome the limitation of this atom-centered description to finite range kinds of interactions, which is particularly relevant for potentials, but also for many additional properties. The polarizability can depend a lot on the overall delocalization of the electron density and so on and so forth. And we are now also implementing a little bit more efficiently than in the benchmark papers to describe long-range interactions that appear to work very well also to capture fairly sophisticated long-range physics, such as that which occurs at the interaction between a polar molecule and a metallic surface. So these are very polarizable system. Yeah, and if you use a short-range descriptor, basically, as soon as the molecule moves outside the cutoff distance of the descriptor, the prediction of the energy can't change any longer, because from the point of view of the descriptors, nothing changes anymore. And using these long-distance equivariants, we can actually model the full asymptotic behavior of the interaction between the molecule and the surface. Now, let's get with this introduction of the mathematical framework that we use, let's move to discuss how you can learn properties beyond potentials. Now, one common feature of properties beyond potentials is the fact that often they have an algebraic structure that is more sophisticated than just a scalar. And for example, you might want to learn response properties that behave like vectors, for instance, dipole moments. Now, if you want to learn a dipole moment of a water molecule, what you would like to achieve is a model for which the predictions for a rotated molecule, so here I have a model for a molecule A, and I'm writing a linear, this is written with this fancy notation, but this is basically linear regression. These are the regression weights, these are the features, and since I need equivariance for my features, I have an additional label that labels the features, and that corresponds basically to the x, y, and z, the Cartesian coordinates of the dipole. Very importantly, the linear regression, so the regression weights, only contract with the index that is not connected with the symmetry, okay? So basically, this is a 3 times n feature matrix, and the weights are just n features. And so each prediction gives simultaneously 3 coordinates of the dipole. Now, what we would like to have is that if now we rotate the molecule, we want the dipole to rotate in exactly the same way. And actually, you can achieve this if you build proper features that transform under rotations as basically the application of a Cartesian rotation matrix. If they do, then naturally your dipole will rotate together with the molecule. So actually this can be built, it works, you can build models of dipolar properties, but more in general, you can use this density correlation framework correlating the symmetry integral with a set of spherical harmonics to obtain a more general set of equivariant representations that transform like your spherical harmonics of choice. Now, this means that you can, for instance, learn properties that are tensorial. The polarizability is a symmetric tensor, meaning that it has 6 independent Cartesian components. Actually, to learn it efficiently, you want to transform it into a more explicitly symmetric form, and specifically the trace of the tensor is a scalar, and it transforms like a scalar. So the trace of the polarizability tensor can be learned with any invariant machine learning model. Essentially, you could use a machine learning potential framework to learn the trace of the polarizability. The remaining 5 degrees of freedom instead transform like a L equal 2 spherical harmonic. So m from -2 to +2. And so by combining all of these, you can build models of the polarizability of molecules that do capture the anisotropy of the polarizability. For instance, if you have a conjugated system, the polarizability in the plane of the conjugated system is much higher than the perpendicular direction. And by doing this, and by training on couple cluster reference calculations, and I have to say thanks to Rob Distasio and his team, because this is really not a type of calculation that I have been able to do confidently. I'm not a quantum chemist. We can basically build a model of the molecular polarizability that in the extrapolative regime, so making predictions for molecules that are larger than those that were included in the training set, beats DFT at the game of predicting the molecular polarizability. You can actually go much more complicated than this, and you can, for instance, learn the electron charge density of a system. And the way we do this, there are many approaches to learn the electron density, but the way we do it is should be very natural to a quantum chemist. And it's basically, we use an atom-centered decomposition of the density, basically using, we compute the coefficient of the density with a resolution of the identity basis. And now these coefficients, since we are using atom-centered basis, transform like the spherical harmonics of the basis. So we need a machine learning model that is covariant as spherical harmonics up to whatever order we choose to truncate the basis. And if you do this, you obtain models that are very transferable. You can actually train them on organic dimers and then use them get a pretty in something like a polypeptide. And given this additive atom-centered nature, the prediction of the density is entirely linear scaling. More recently, in collaboration with Mariana Rossi, we have been also able, and this is actually not a big conceptual change, but in terms of implementation, you know, it was not a walk in the park. We could extend these to the prediction also of densities in the condensed phase. So conceptually, there is no difference, but, you know, we had to move to a different software. We had to care about periodic images. So there are some subtleties, not so much on the machine learning side, but from the point of view of expanding the density in an atom-centered basis. And something very, very recent, just put in the archive a little bit more than a month ago, we have also built a entirely equivariant, which means equivariant with respect to rotation, translations, and permutations of the indices, a model for the matrix elements of the Hamiltonian written in a atom-centered orbital basis. And so what I want to emphasize with this figure is the fact that if you want to build an equivariant model, it really pays off to start by obtaining the most symmetric representation possible of your target. So here we decompose the Hamiltonian into combinations of elements that are permutation equivariant. And then we also decompose the blocks of the Hamiltonian, because, for instance, if you take the Hamiltonian, this transforms like a product of spherical harmonics, and so you want to decompose it into irreducible components that transform like S. These are basically the same as for the polarization and polarizability, sorry, and then you also have a P component in this case. And what I want to emphasize is that, you know, incorporating all these symmetries is something that really pays off. And as I have this neat example in which we take benzene in a minimal atomic orbital basis. So really think, you know, Huckel model from your undergraduate years. And we fill a matrix, which is 30 by 30, basically corresponding to a minimal basis representation of the electronic structure of benzene, and we fill it with random numbers. And then we try to learn this using this model. Now, this model doesn't know explicitly anything about D6H symmetry. Still, given that it incorporates all the fundamental rotation and index permutation symmetries, is intrinsically D6 symmetric, which means that it cannot learn a matrix of random number. The prediction that we get after having trained on a matrix of random number is very different from the starting matrix and has all the right symmetries. And this has important consequences because the value of the energies of the eigenstates are just random, but the symmetry of the molecular orbitals and the degeneracy of the molecular orbitals are the ones that are prescribed by molecular orbital theory for a D6H molecule. And I want to stress that this is really helpful for machine learning because you also incorporate not only the behavior of ideally symmetric structures, but also the behavior of the eigenstates when you deform your molecule. So basically, Jan-Teller theorem is built into the model without explicitly specifying what is the point group symmetry you are expanding around. So having built these models that allow you to predict energy and forces with first principle and also to predict other properties means that we are now in the position of doing fully integrated machine learning modeling of pretty complicated systems. And this goes from using only the energy and the forces, but use them to predict finite temperature thermodynamics. And here I'm showing this example of water. I'm very attached to it because water is a really tricky system, and it also requires describing the quantum mechanical nature of the nuclei, which is something I like a lot because it's what I did when I was a postdoc, so I really like it. And basically using a combination of machine learning models and thermodynamic sampling, we can get without any fitting parameter, we can get the melting point of water within 5 Kelvin. We get the difference between the melting point of H2O and H2O, and we get the difference in free energy between cubic and hexagonal ice that are incredibly close. So this is really, really challenging calculations. Now, you can also use these, given that we can predict also other properties, for instance, NMR chemical shieldings, we can also investigate the role of finite temperature fluctuations on something like the NMR chemical shieldings of nuclei in a molecular material. And these can be used then to get more accurate predictions and more accurate comparison with experiments, which is very relevant because you need it to use NMR to do crystallography, basically. And then, given that we can provide machine learning models that predict the IR spectrum or the Raman spectrum of liquid water, and this is something which, with a very, very big computer, you could run brute force with first principles DFT calculations, but now we can do it, comparing different exchange correlation functionals. And what I really like is that this paper is not about these graphs. So, it's something that you can now do sort of, yeah, whatever, we are doing a paper on quantum dynamics in the condensed phase, and we do it with a machine learning model that does everything. So this is something what I really like about this figure is that that's not the main point of the paper even. And something which we are doing more and more now is also to learn the electron density of states. And this is interesting because you can use it to incorporate finite electron temperature properties into the thermophysics of materials. So this is the heat capacity curve for nickel, and there is an incredible amount of physics in here. There is freezing of vibrations in the quantum regime. There is the Curie temperature, so the end of the ferromagnetic order, which we are not modeling. But at high temperature, you also have a contribution to the heat capacity that comes from electronic excitations. And in this paper, we basically get this contribution without doing additional DFT calculations, but using a model of the electron density of states. And the electron density of states can also be used, for instance, to get an idea of the electronic properties of a material, and this is really a paper by Volker-Deringer. We gave a very small contribution to it, but I think it's a nice contribution. So they had a model they could use to simulate the behavior of amorphous silicon under high pressure. So they had a full description of the structural properties, but experimentally, the way you probe this system involves computing, measuring the conductivity. And so what we could do was to predict the conductivity by using the density of states as a proxy for boxes with 100,000 silicon atoms simulated for tens of picoseconds. And we could basically compute the density of states with hybrid DFT accuracy, and it would be, I would say it's fair to say that it's out of question to compute HSE0 over a box of 100,000 atoms. And very recent, this basically appeared on the archive a couple of days ago, we are now also probing the behavior of more complicated functional materials, and this is these are plots of the polarization of barium titanate as it undergoes this series of phase transitions that occur when you go from the paraelectric cubic phase through a sequence of different ferroelectric phases, and everything here from the energetics to the polarization are computed with DFT trained machine learning models. So I want to, for doing so, just a couple of slides to tell you that one, all the computation technology that goes behind these papers is available on GitHub. We have a sort of a federation, a modular set of files that we use to do this. And I also want to thank the members of my group because they were instrumental in everything that you have seen. And in particular, they have put a lot of work into making this software easy to use and decently documented. This is actually half a group because we are still in mixed COVID mode. Yeah, as a basically general conclusion, I hope that you have appreciated how throughout I'm trying really not to treat physics-based and data-driven approaches as competing paradigms of chemical modeling, but I'm really trying to use them together, getting the best of each. And I think that there is a lot to be achieved by basically making machine learning an integral part of the modeling toolbox. You know, not better, not worse than a full explicit first principle model.